Friends, in the last class we talked about the space lattice in the crystal geometry, and today we shall start with the crystal structures and then move on to the crystal directions and planes in three-dimensional crystals. We defined the space Bravais space lattice is only 14, but as we know there are thousands of crystals already known to us and they are listed in the literature. So with the help of this 14 space lattice we have to understand these various crystal structures. To define the crystal structure as space lattice and basis. As I said earlier, before I started defining these space lattice, said crystal has a periodically repeating arrangement of atoms or group of atoms. So to understand that, we first saw the arrangement of points, geometrical points in three-dimensional space. Having seen that, now we shall associate with each point which was a geometrical point, no physical entity, a group of atoms or molecules, what I am calling motif or the basis of the crystal. Okay. Now this basis is the simplest if I have only one atom in it. I don't have to define anything except saying it is a copper atom, or it is an iron atom, or it is a zinc atom. So I have to just specify that the kind and the number is only one, it becomes very easy. But once the moment I have 2, 3 or more number of atoms in the group which is sitting on every lattice point or associated with every lattice point, I need to define number of things. I need to define number of atoms and their kind. I need to define the spacing between those atoms, that is internuclear spacings, how the group is arranged. Then how this group is oriented in three-dimensional space. Let us say, what I mean by orientation will become clear to you after I show you some pictures. I have this group which forms, let us say, joining the centers, a figure like this or a triangle. Is this triangle arranged like this, or this triangle is arranged like this in space? That is what I mean by orientation. I am sorry. That is what you have to see. So we have to understand the orientation in space, that we shall see with the help of simple examples. Here I show you one very simple example of a simple cubic space lattice. Lattice points are at the 8 corners of the cube, and I associate one atom on every lattice point and I get a crystal unit cell like this. See, if I associate with the same space lattice set of 2 atoms or a group of 2 atoms, the motif contains 2, one is this atom, the other one is this. This is associated with each lattice point in the same orientation, and the spacing between the 2 atoms, center to center distance, is also the same. Center to center distance between them is same everywhere. And the line joining the center to center, if you see the orientation in three-dimensional space, is the same. As a matter of fact, it is possible for me to join the centers of the smaller spheres and make a unit cell which is identical to the already drawn unit cell. So I need to define, when we have 2 this is atom of one kind, this is the atom of the second kind. I have to name them. It could be a copper atom, this could be a zinc atom. Okay. Then I have to define the distance between them. Well, for that I shall explain to you that these atoms, while trying to understand the crystal structure, we are going to assume that they are hard spheres. Though we know from the knowledge of chemistry that there is a nucleus around which there are number of electronic orbits, and these electronic orbits are not solid, in the sense they are compressible electron clouds. They can be extended too, but we shall assume these to be hard spheres for understanding the crystal structure, the periodic arrangement, and whenever it comes we will try to know that yes, it is not a hard sphere. So, this is the internuclear spacing is defined, and then orientation in space is got to be defined, right. I shall show you another arrangement where the two atoms are there associated with every lattice point, but the orientation in space is different, internuclear spacing is different, crystal we get is different. See the same thing. In here, this same unit cell shown here. Now, the two atoms are arranged, internuclear spacing is half the body diagonal of the cube, and the orientation is along the body diagonal of the cube. This crystal looks very different from the previous one, though there are only two atoms associated with every lattice point. Here you will ask me, where is the second atom associated for this? It has to go to the next unit cell. From there I have to go to another unit cell. Each corner I have to go to another unit cell to find that, and this forms a different crystal altogether, though I still have the two atoms forming the motif, but the motif is different. It is oriented in space differently. I get a different crystal. Right. This one example could be that of cesium chloride. This could be the cesium ion sitting here in the body center, and these are the chloride ions sitting. I got a cesium chloride crystal like this. So, we see that motif or the basis, the group of atoms has to be associated with every lattice point. I get a crystal, right. Well, as I already said, the simplest of the arrangement could be in the motif only one atom, and 2, 3, 4 they are going to form a little more difficult motif, but there is one element from group 7 which is manganese. It shows number of allotropic forms. One of them is alpha manganese. At room temperature, the space lattice is body centered cubic, and there are 29 atoms in the motif, 29, not 1, 2 or 3. There is second form of the manganese, the body centered cubic, the beta manganese form. The space lattice is simple cubic, and there are 20 atoms sitting on the motif. But if I go to some of the polymeric crystals or maybe protein crystals, there could be 10,000, 20,000 atoms in the motif. There are more complex structures. We should restrict ourselves to common materials which we are using, and they have 1 or 2 atoms in the basis usually, and the motif is simple. We will be able to understand that. Now, talking about the hard spheres, we define the diameter as the distance of nearest approach. So, for example, I just showed you one unit cell, let me show you another one. Here the atoms, this is let us say a BCC space lattice, and I have this motif as one iron atom. It is sitting, one iron atom is sitting at each lattice point, which are at the 8 corners and one body center there. Right. So, this becomes BCC iron crystal. The distance of nearest approach is not the atom from one corner to another corner, but one atom from the corner to the body center. That is the shortest distance between the two iron atoms, and this distance is half the body diagonal. If lattice parameter of the unit cell is A, it is under root 3 by 2 of A. This is equal to the diameter or the twice the radius of iron atom. That is what I mean when I consider them to be hard spheres. However, like the example I showed for cesium chloride, this atom is different from the other one, then the radius of this plus the radius of that shall become half the body diagonal. Again, that is the meaning of the hard spheres. I consider them to be hard spheres, okay, so that we understand the crystal structures well. Alright, with this knowledge of the crystal structures and the arrangement of points in 3-dimensional space, now I am interested in looking at the directions. After the points in geometry, you are always taught the lines, but instead of lines, here I am interested in direction. Direction is a line, alright, but it has a orientation, which we always show with the help of an arrow. It will show the sense of the direction if I show the arrow, okay. So, we give the names to these directions in crystal, and these names are called Miller indices. We give names to all parallel directions in the same orientation or same sense, one name. All parallel directions which may be there in the crystal pointing in one particular direction, they are given one name. If they are pointing in the opposite direction, the name would be opposite. What is that opposite? We shall see that. For this, how we go about is, we first of all choose the origin, and the choice of the origin is arbitrary. Normally, we put the origin at the lattice point, and if there is a unit cell which could have one lattice point per unit cell, 2 lattice points or 4 lattice points, depending upon where the lattice point is, I can choose my origin. This choice is arbitrary and left to the user, okay. And you can, in the same crystal, understanding one problem and the other problem, you can shift your origin, or trying to know one direction and the other direction, you can shift the origin. But the axis and their sense, once you choose, you will not change, otherwise you will lose the relationship between various directions, okay. So, therefore, axis and their sense, once you choose, again the choice is arbitrary, but once you have chosen, you will not change them for looking at the problems of the same crystal, okay. Well, let us say I choose the 3 directions A, B, C here, and that is my origin. Right, this is how I choose my 3 directions A, B, C. The fundamental lattice translation vector would be from the origin up to the end of the unit cell. That distance is 1 unit from here to there. That is 1 unit. It could be 3.5 angstrom, it could be 4.2 angstrom, depending on what space lattice it is. What is A, B, what is C? It need not be 1 angstrom, it need not be 1 centimeter, it need not be 1 millimeter. Mind it, it is a unit distance along the direction A in the space lattice, and that is from one lattice point to the next in that direction, and that is my unit distance here. And similarly, the unit distance from origin to B is here, unit distance from this to this is there. These are my unit distances along A, B and C, right. That is important because we will be talking about these unit distances 1, 2, 3. Then in the unit cell, if I had point, I can always define the position coordinates of a point. So for example, origin, what are the position coordinates of the origin? 0, 0, 0. But my order is always A, B and C. Let us say for example, I want to find out what are the position coordinates of this point. Let us call this point X. It is going to be 1, 0, 0. That is the position coordinates. Similarly, I want to find the position coordinates of this point. Let us call this point P. It is going to be 1, 1 and 1. Those are the position coordinates of the point. Anywhere in the unit cell, it is possible for me to find out. Let us say I find out the center of the front face. What are the position coordinates of this? Along A, I have to 1, along B it is half, along C also it is half. Those are the position coordinates. Is that clear? Right. All right. Now I call that A, B and C. Somebody can choose the origin here and call this B, call this as A, call this as C. I have no grudge, it can be done. That is what I said, since axis you can choose arbitrarily. If required, you can shift your origin from here to there. In that case, you will have your A going from here to there, you will have your B moving in that direction, and you will have your C moving in that direction, right. Sense is not changed, that is the meaning of the axis. Once chosen, the sense is not changed. All right, let us, having done that, let us try to find out the Miller indices of a direction. I will show you the two ways in which we can work with it. I have the direction in this unit cell which is given here. Let us say I am interested in finding out the name for the direction, let us call it P Q. I am interested in finding out the direction PQ. So the one way of doing this is, let the tail coincide with the origin. This can be done in two ways. Either I shift the direction parallel to itself and let it pass through the origin, like the one I have shown here. Let us call this direction O, and this is, let us say, what do we call it, R. OR is the same direction PQ, as simply shifted parallel and passes through the origin. Okay. Or another way is, you push your origin at P to coincide with the tail of the direction arrow. Arrow has a tail and the head. Okay. So and then we can try to work out the name of this. But however, as I said, we have to choose the direct sense of the axes which we are there. Let us call them A, B and C, right. Let us go to the this is what after shifting it is the position, and I have called this as A, I have called this direction A, this direction B and this direction C, and that is my origin. I have to determine the position coordinates of the head of the arrow. What are the position coordinates of the head of the arrow? On A you are going distance half, on B you are going distance 1, and on distance C you are going gain half distance. Since the tail is at the origin, reduce them to the smallest integers in the same proportion. That becomes 1, 2 and 1, and close these in the square brackets. These are the Miller indices of this direction OR. In other words, that is the name of the direction OR in the crystal is 1, 2, 1. And unknown indices are always written as HKL. We do not write XYZ. Axes we are not using XYZ. Indices are called HKL, unknown indices, and the three directions we choose as A, B and C other than XYZ. Generally XYZ you get the connotation of Cartesian system. In crystals we do not have always the Cartesian system. Cartesian system of axis will be working if I have a cube. It will not work even if I have a tetragon, because A is equal to B but not equal to C. So Cartesian system is not working there. In Cartesian system I, J, K, all three unit vectors are equal in magnitude. In my case they are not in crystals, therefore we are using A, B, C rather than X, Y, Z. Okay. Well, for the same direction again, actually the direction I said was P to Q, which I shifted from O to R. I want to find out this direction actually. Now I do not want you to pass it through the origin or shift the origin. Rather I ask you to find out the position coordinates of the head, position coordinates of the tail, and subtract the position coordinates of the tail from those of the head. Let us see what do we get. In this case, this is my origin, again A, B and C. Now the position coordinates of the head, or which is Q, is 1, 1 and 1, and position coordinates of the point P are half, 0 and half. If I subtract the position coordinate of the tail from those of the head, I get 1 minus half is half, 1 minus 0 is 1 and 1 minus half is half, and I have to convert them into integers in the same proportion and close them in square brackets. I get 1, 2, 1. And here another thing which I am to say, that between 1 to 1 I do not put any separator, no comma, no colon, no space. This is required only when I have some irrational direction which may have 2 digits, say for example 2, 11, 3. So if I try to write 2, 11 and 3, unless I separate them like this, or I simply write it like this, somebody can read it as 21, 1, 3, somebody can read it as 2, 1, 13, so 2 be clear, we do this, use this separator, otherwise we do not use the separators when they are usually single digits, right, and most of the times we are this kind of directions where we do not have to use the separators. Let us look at a direction 2 bar 2 1. Now I have to, well, what is this bar business here? So far I have showed you the direction where A, B, C components were positive. Now if any of the component becomes negative, then we don't show this negative by putting minus in front of the in this index, rather putting that minus on top of the index and call it bar. Like minus is read before the integer, here also bar is read before the integer. So I read it as 2 bar 2 1, 2 bar 2 1. Alright. So let us again use the same origin here, A, B, C. I am not changing the sense of the axis for this, but now I want to know where is this direction 2 bar 2 1. Firstly, in a unit cell I cannot have any distance in terms of the position coordinates 2, it can be maximum 1. So I must reduce these indices to maximum being 1, but in the same proportion. That becomes 1 minus 1 and half, but these are not indices. Starting from origin, I must locate a point which has the coordinates 1, minus 1 and half. If I do that, I will go out of the unit cell now. Minus half on B, I shall have to go on to the left. I will have to go out of the unit cell in this direction. So what I do is I shift my origin without changing the sense of the axis. I keep my origin somewhere here. If I take my origin there, this is the B axis, this is the A axis, and this is the C axis. Now let us find out the position coordinate of a point 1 minus 1 and half. 1 on A is here, minus half, minus 1 on B will be there, and plus half on C will be here. That is the middle point of this axis, and therefore I join it from this to the origin and show the arrow like this. That is the direction 2 bar 2 1. Is that clear? Now tell me, what is this direction? Now I am asking the problem other way around. I showed you an earlier example. Pardon? Look, starting this, if I put my origin here, on A I am travelling plus 1, on B I am travelling minus 1, on C I do not travel at all. So this direction is 1 bar 1 0. Good. That is the direction. So you can work out more examples like that. Right. Then in the crystals we have family of directions. Family, by family what I mean is a direction which looks physically identical to another direction and not parallel to it. If it is parallel, it is the same direction. It looks physically identical but not parallel. Say for example, I talk of a face centered cubic crystal, right? In face centered cubic crystal, try to look at the face diagonal. The distance between two atoms you will find is a minimum distance between two lattice points, and there is a minimum distance between two atoms, that is the diameter. It looks something like this. It looks something like this. And one of the phase diagonals I just showed you is of the kind 1 1 0, and a one which we have named was 1 bar 1 0. You can also find out something 0 1 1. They will, all these phase diagonals will be looking like this. Are they parallel? They are not. Let me just show you again a simple this is a cube. I just show you the front face of the FCC. This is one diagonal, that is another diagonal, and as per the definition, this is the smallest distance between the two neighbors. So the spheres must be touching actually. They must be bigger than that. Okay. That is how it looks like. So this direction which I am talking about, the diagonal, or it is this diagonal or it is that diagonal, they will all look like this. They all form a family. When it is a family, we represent it not like this, we represent it by carets, and within the caret we put indices of any one of them. Any one of the members, I can put the indices inside the carets, it represents all the family. Now how many members do you think in a cube would be there which are the phase diagonals? On this face I have 2, but this is an opposite one, this is an opposite one. So this will become 4 if I look all of them. So there will be 12 members. 4 of these, 4 on this face like this, and 4 on the top face. They will all look alike. Out of these, 6 are non-parallel. Remaining 6 are opposite of these, right? And this, if you try to expand this in a cube, ABC are equal, ABC can be permuted. So 0 1 1 if you permute can become 1 0 1, it can become 1 1 0, that is how you have permuted 0. You can make one of them negative, let us put this here, can make one of them negative, it is like this or like that, or similarly you can make the other one, or you can make in the second the last one, nor you can make 2 of them negative, right? There are only 2 ones, both of them can be made negative, like this. How many I have made? 12. This one is opposite to this, this one is opposite to that, this one is opposite to this, and if these are talking about the individual directions, I must put the square brackets. So on and so forth. Right. This I talked about one direction. There could be another direction in the same crystal. Let us talk about the edges of the FCC where atoms are not touching. This distance is more than the diameter, and since I am considering them hard spheres, there is a space between them. This space can be small, this space can be large, depending upon which direction I am looking at. Unless the direction is like this, all other directions could be with some space, or it could be something like this. They are all different directions, they will have a different name. Characteristics of the crystal in these different directions will be different. That is why there is a need for us to give them different names. All right. Now let's have some examples of the family. I'll take a simple one. I have taken already one, the phase diagonals. Another example we take of a family 1 0 0. To the permutations, the members are going to be 1 0 0 0 1 0 and 0 0 1, and the opposite of these bar 1 0 0 0 bar 1 0 and 0 0 bar 1, right. So if I again choose this as the origin, that is my A axis, this is my B axis, this is my C axis. Where is one the first direction? 1 0 0. This is the direction 1 0 0. Right. Where is the direction 0 1 0? This is the direction 0 1 0. And that is the direction 0 0 1. Now, what is this direction? We will call it bar 1 0 0. As I said, bar is to be read before the digit. Okay. If I read it 1 bar, then I am talking about the bar of the second digit. It's the bar 1 0 0. Okay. Right, like that you can find out the rest of them. Now, after having a look at the directions, the families of directions, we shall look at the planes, geometrical planes in the crystal. In case of planes, like in case of direction, a set of equidistant planes, a set of equidistant parallel planes. They are equidistant, the whole set is a set of parallel planes and they are at the same time equidistant. Like say for example, I talk of this set in a given crystal. This set and the distance between the consecutive planes is, let us say, is d. That distance is same to the next. But here is the same set parallel in the same crystal, but the distance is different. Let us say it is d by 2. So, this set and this set will have slightly different name, though they may be related names, but they will be different. So, set of parallel equidistant planes is represented by a set of Miller indices. These are also called Miller indices. Okay. And of course, on changing the distance, as I showed here, the name can change, and but if they are parallel, the name would be related. Okay. Now, for doing this, what we do is Again we choose the origin in the, we refer to unit cell again, choose the axis and the sense, and the choice is arbitrary, and then what we work out are the intercepts made by the adjacent planes, because origin is taken on one plane. Let's say, for example, here there are 3 planes, 1, 2 and 3. I choose the origin on the middle plane, then I find out the after making the axis in the crystal, what are the intercepts made by this plane on those 3 axes. Or if I have chosen the origin here, I find out the intercept made by this plane, right. There will be slight difference in the name when we find out for this one and that one, because once the origin is here and the axis have been chosen, if the intercept made by this is +1, intercept made by that one will be -1. So if there is a plane HKL, this one is named as HKL, this one would be named bar H, bar K, bar L, but in our mind we know it is, we are talking about the same set of planes. One is on one side of the origin, other one is on the other side of the origin, and origin is taken on one plane, okay. But I cannot find out the indices of the plane on which I have chosen the origin, because the plane is passing through the origin. It is not possible for me to find out the intercepts made by it on A axis, B axis and C axis. It is not possible. Is that clear? So that is what we are going to do. So intercept made by the adjacent plane are determined, right. All right, let me choose a plane here and then we shall try to find out its intercepts, okay. The plane let me choose is in the crystal. This is a plane, right, and I choose my origin here. Let us call this as the A axis. Now let me change my sense of the A axis, B here, and let us call this one as C. I want to find out the intercepts made by this plane on A, B and C, right. All right, so how do we go about doing that? That is my origin. Intercept made by this plane on the A axis is how much? 1/2, okay. Unit is again from 0 to 1 here. What is the intercept made by it on the B axis? B axis lies on the plane, it goes up to infinity. So it meets that plane at infinity, okay. So intercept made on the B axis is infinity, and what is the intercept made on the C axis? 1. So this is half, this is 1, and there it goes parallel, right. So let us go and see how we name this plane now. Once I have found out the intercepts made on the, again we write the order is same, A axis first, B axis and then C axis. So order let us write what has happened to the other one. You slide in between. There was a slide in between gone somewhere. I don't know what is happened. All right. So the 3 axes let us write down. A, B and C in that order. On A we found out the intercept to be half, and on the B the intercept we found it to be infinity, on the C the intercept we found it to be 1. Second step is we have to take reciprocals. Reciprocal of half is 2, reciprocal of infinity is 0, and reciprocal of 1 is 1. If these are integers, we do not do anything about it. If these are not integers, we multiply by an integer to make them integers, and we multiply by the smallest possible integer, which you can find out by taking the LCM. Okay, and then these are closed in parenthesis. That is the name of this plane which I have chosen, 2, 0, 1. Is that right? You name this plane as 2, 0, 1. All right. Well, this is maybe an example for us to see the Miller indices of this plane. Let us do that. I choose my origin again here. Let us call this as the, what we call this, A axis we called here, we call this as the B axis, we call this as the C axis. All right. Now this is the plane which is chosen, passes through the origin. So I must shift the origin to another plane parallel to it. Okay. So therefore let us take the origin here, shift the origin, sense of the axis is not changed. So what intercepts does it make on A, B and C? Now let us see. From starting from the origin, this plane intercepts the A axis on +1. Starting from this origin on the B, it intersects here, which is -1. Starting from this origin on C, it intersects here, which is +1. Reciprocals 1, -1 and 1 are the reciprocals. These are already integers, and minus will be kept on top and read as 1, bar 1, 1 and close in parenthesis, right. All right. Next example to put is, now the plane is given to bar 1, 1, 0, name is given, but to locate this. Again let us choose the origin, axis again A, B and C. If it is not the same crystal, it is a different crystal, you can always change the axis, right, but let us consider the same unit cell, bar 1, 1, 0. Now what I have to do is I have to first take the reciprocals of the indices. I am going to opposite direction now. Reciprocal of this is -1, reciprocal of is 1 and 0 is infinity. So I have to make the intercepts -1 on A, 1 on B and infinity on C. I mean the plane is going to go parallel to the C, right. So starting from origin, if I take -1 on A, I have to go out. So I shift my origin from here to there. Then -1 on A, the intercept is here, +1 on B, the intercept is here, because B axis is going to be here, that is going to be B. So these are the two intercepts and it is going to run parallel to C. So join these two intercepts and run parallel to C from there. I am sorry, this has turned out to be just a line, this whole plane. Well, you will see that this plane, it is possible for me to show you much better than this if I change the sense of the axis or the axis in themselves. Say for example, I name well, I am not able to do that. Let us call this one as C and this one as A. Let us make this change. Now, if I have to do this, my origin will be here. -1 intercept on A, I shall go there, +1 intercept on B, I shall go here, and parallel to C I have to run. So, join these intercepts, sorry, run parallel to C from here. I am sorry, I will have to rub the few lines here, provided I can rub. Okay. All right. That's the plane I have. Right. So, this is the plane. Now, you can see that plane. Earlier it was just becoming a line, you were not able to see that because of the cube, the way it has been drawn. So, this is depends upon how we are viewing it, that is what we go about sketching the plane, and that is bar 1 1 0 plane in the unit cell. Like we had the family of directions in a crystal, we also have family of planes. There could be sets of parallel planes which are equidistant, but not parallel to each other, but differently oriented in space in the crystal, and they may be looking alike. Before I proceed there, let me just talk about this plane itself, bar 1 1 0, and in this bar 1 1 0, let us talk about an FCC. One atom is here, another atom is here in FCC, and this is the phase centers. If I make them little bigger ones, they can be made to touch like this. So, these are the arrangement of atoms in the bar 1 1 0 plane in FCC. Similarly, let us look at a plane in the same unit cell which is 1 1 0. Which is 1 1 0 here. Intercepts are 1 on A, 1 on B, infinity on C again. Intercept starting from this origin, 1 is A here, 1 is B there. So, it will be a plane like this. In here the atoms are arranged beside this phase center, they are arranged here. So, if I look at the two planes, both the planes look like this. This distance is equal to the lattice parameter A, this distance is the phase diagonal equal to under root 2 of A, is a rectangle, and atoms are arranged in these locations. Sorry for the reason of clarity, I am not making them touch, otherwise they will become little clumsy. So, this is the arrangement, whether it is a bar 1 1 0 plane or it is a 1 1 0 plane. You will see the same story if the plane is 0 1 1 or the plane is 1 0 bar 1 or any other member of the family. This is what we call a family. They are not parallel, but the arrangement of atoms is same, the physically identical planes. So, characteristics of the crystal on these planes will be similar. So, family of planes is what we call them, and this family of planes by the curly brackets or the braces, right. Let us say what this family 1 0 0. Again, this is my direction A, direction B, direction C. 1 0 0 is the front face. From this, the another member would be 0 1 0. 0 1 0 is this right hand side face. Another member would be 0 0 1, that is the top face. Similarly, you would have other member bar 1 0 0, the back face. You will have the member 0 bar 1 0, the left hand side face. You would have 0 0 bar 1 bottom face. Okay, all the 6 faces form a member, they all form a family and they are not parallel. You can see that. Only 1 0 0 is parallel to R1 0 0, and that I told you. One is taken on the one side of the origin, other is taken on the other side of the origin. So we are talking about the same set of places. All right. Now quickly revise what we have talked about. Unknown Miller indices are represented as HKL for single direct square brackets. For family of directions we use carets. For planes we use parentheses, and for family of planes we use braces. Well, we only when one of the index happens to be of 2 digits, we use a separator, maybe a comma. Otherwise, separator is not used. Negative indices, we put the bar on top and read it as bar 2. Members of family of directions are not necessarily parallel, and similarly, members of a family of planes too are necessarily parallel. Okay. By the indices, we can change the directions opposite to each other. So for example, I just given the example of a direction. Let us say 2 1 3, and I have bar 2, bar 1, bar 3 is opposite to this, right. Similarly, planes, by changing the sign, it's the same set, it's not different, but only thing is one is on one side of the origin, other is on the other side of the origin. That is, let's talk about 1 1 1, and the other one is bar 1 bar 1. They are parallel, right. Alright, so stop here.